Last time we were talking about Bayesian networks, and let's just do a bit of a review. There was some confusion on one aspect which I'd like to cover. After that, we will now go on to the next topic, which is probabilistic reasoning over time. Okay, and we started this off last time talking about stochastic processes, which has time involved, random variables plus time. And then we spoke about Markov chains. Well, we didn't really start talking about Markov chains last time, but we hopefully will get a chance to do that today. And then a somewhat complex topic, which is Markov decision processes. Okay, but it's a very critical topic as well if you want to get involved in AI and also reinforcement learning and machine learning as we go forward. So I will be spending hopefully today's lecture and the next lecture at least on MDPs as well. So it's an important topic that you need to pay particular attention on, and it's a little complex as well. So let's go forward. We spoke about conditional independence last time. We also spoke about marginalization. And this is linked to one of the problems that we ended up having in the last lecture, where we said that marginalization of probability of A can be derived from the joint probability. And let's say if you're trying to get rid of this other variable B, then you sum the joint probability or all the other possible values of B. So for example, if you want to get probability of A, you take probability of B and you take probability of B bar. Okay, so you take the joint probability, this is the joint probability, and you sum over all the possible values of the variable that you're trying to get rid of. Okay, so far this was okay. Where we did get into a bit of difficulty is when we made it a little bit more complex. In other words, what we were trying to do is we had two conditional variables, B and E, and we were not just trying to get the probability of A, but we were trying to get the conditional probability of B of A given B. Okay, and this is a little complex, so we did get a little confused about this. So in order to solve this, and I'll spend a few minutes on this again today, we need to first be able to figure out what's the probability of A given B. If you've given probability of A given B, how do you determine the probability of A? Okay. Now, is this something that you've already seen? Finding the marginal probability of A given the conditional probability A given B. Do you recall having seen this before? We have seen this before. In fact, when we talk about Bayes' theorem, we use this in the denominator. Okay, if you remember that. So if you recall, we had this equation when we were looking at Bayes' theorem, and we looked at the probability of B in the denominator, and we said the probability of B is simply the probability of B given A multiplied by probability of A, and similarly plus probability of B given A bar multiplied by probability of A bar. Okay, so you've already seen this. It was sort of understood at that point, but let's try to see how do we actually derive it using the marginalization equation. Okay, so the marginalization equation is that if you want to get the probability of A, you take the joint probability, okay, not the conditional probability. This has to be the joint probability. And this is where we got perhaps a little confused last time. We started working with the conditional probability and we summed it over all the probabilities of B. And we got a different answer and we were trying to figure that out. So the important thing is that this has to be the joint probability, okay, when you're trying to do marginalization. So let's just use that and see where do we get. So we're trying to determine, so the first question is that in order to solve this equation, this problem, we're going to try to determine what is the probability of A given probability of A given B. And as I said, we already know this, but let's just derive it using marginalization. So the marginalization equation says that the probability of A, if you want to use the joint probabilities of A and B, then simply use this equation. And if you use this equation, then what you can do is, remember from the chain rule, if you want to convert this into a conditional probability sum, then what you do is you use the chain equation. And the chain equation basically said, the chain rule said that the joint probability can be expressed as the conditional probability multiplied by the marginal probability of B. Okay, we've already seen this. So all we need to do is substitute this chain rule inside the joint probability, and this is what we get. Okay, so it's almost obvious, but since we did get confused about this last time, I thought we need to just make sure that, you know, if I got confused, I want to make sure you guys don't get confused. Okay, so you can't just remove this and say that the probability of A is equal to the sum of probability of A given B and sum over all B. This is where we sort of got confused and we said, why isn't this working? And that's simply because we were trying to sum over the conditional probabilities instead of the joint probabilities. Okay. So anyway, this was worth spending a few minutes on to recap. The rest of it is well, okay, we still haven't solved the original problem. So now the question is, how do you determine probability of A given B given that you have this problem? Okay, now you have two conditional probabilities, B and E. And where did this come from? This came from basically from the example of the earthquake example, or you may call it the burglary or the alarm problem. Okay. And we were trying to find out what is the probability of A given B, given that you have not just A given B, but you have A given B and E. Okay, so this was what we had, and we were trying to determine this. So now let's try to see if we can use the what we already have derived so far. So we already know this now. Okay, so this is something that we've already determined, that the probability of A can be written as the sum of the conditional probability with the joint probability of B. Okay, so we can write it as a general equation over here. Probability of X is simply the conditional probability given some other variable Y over the marginal probability of Y. Okay, this we've already got. Now what I'm suggesting is that to be able to solve this, let's make a few substitutions. Okay, instead of X, we're trying to find this. So let's just make X equal to A given B. So we make X is equal to A given B. We make X the conditional probability. And in this original equation, this is now X. Okay. And we had X given B. So let's replace, let's make Y equal to E. Okay. So we can simply say that the probability of A given B is now, this is directly from here. Okay. And this comes out from here. Now you might say, are these two equivalent? Probability of X given Y, is this equal to, let me write it over here, probability of X is A given B given E. G. Yeah. Bar after? Yeah, okay, so that's what I'm doing over here, right? So basically what I'm saying is that, are these two equivalent? Is this equal to probability of A bar, not bar, but this is given, okay? A given B comma E, okay? Are these two equivalent? Well, actually they are, because all you're saying is that A given B given E, and in this case, all we're saying is that we're basically trying to determine A, and we're sort of clumping these two together. Okay, we're saying that we need to find out what the probability of A is given all these other things. Okay, so we can actually remove this over here. So this essentially becomes, if we make these replacements, X replaced with A given B and Y replaced with E, then this equation simply becomes this equation. Okay. So work this out as well and make sure that you understand this. And if you're not convinced, we can discuss it again. But this is essentially what we used last time. And if you remember, what we did was we wanted to get probability of A given B, given this conditional probability matrix. And so we did 0.95. Remember this? This is just a revision, multiplied by the probability of E, okay, 0.002, and then 0.94 multiplied by the probability of E being false, okay, which was 1 minus 0.002. So this is, and the rest of it simply continues from where we left, okay. The only confusing part was how did we actually get this part, okay, in other words, this whole part. So that was a bit of a clarity, and the rest of it, again, probability of A was also derived in a similar way, same continuation, except that now we have a probability of B and E. Okay, so continuing on, then we looked at the application of Bayes' theorem to get a causal relationship. And then we looked at joint probabilities, and we looked at several examples of those. And then we had equation 14.3, which was also important, that if your if the parents are a subset of the conditions, then you can remove the other conditions. And then we said that this is a little bit more complex, and it certainly is. And I'm not going to spend too much time on this. And as I said, that the book also does look at it. It looks at the particular condition probability of B given J comma M. In other words, what if both John and Mary call, then what is the probability of a burglary having happened? Okay, and this is a little lengthy, so I'm not going to go with that because I think, as I said, there are solutions, technical software solutions for being able to solve more complex problems. But the basic thing is that you need to understand the basics, and then you can keep on extrapolating that. Okay. So now let's start the topic of probabilistic reasoning over time, and we started talking about what stochastic processes are. Okay, and we said that there are, you could perhaps divide the stochastic processes into 4 different categories. And these were the cases where, since you have 2 variables now, basically this is the stochastic process. It comprises of X, and it's varying over time. So X is the random variable, and T is the variation over time. Okay, and so the time itself could be discrete or continuous, and the value of the random variable itself could be discrete or continuous. So you have 4 possible combinations of stochastic processes. Okay. And we started looking at various examples that you guys gave. And let's just continue on from there. And first, let's try to understand what the 4 categories really are. Okay. So, so if you look at these 4 categories, this is the case where the time and both X are continuous. So you can see that I haven't shown any grids over here. Like I have shown over here, and there are no tick marks over here as I've shown them over here. Okay, so this is continuously varying both in time and the random variable. The second case was where you have X being discrete. So X can only vary over these 3 values. Okay, so it can either have, for example, this could be 1, 2, and 3. So X can only have the values 1, 2, and 3, for example. Okay, so you notice that whenever I'm jumping, I'm going from the value of 1 all the way up to the value of 3, and then to 2, and then back to 1. Okay, I'm not jumping in between. So it can only have discrete pre-specified values. The third case was when X is continuous, but the time is now discrete. Okay, in other words, you can only have changes at these discrete times. Okay, you can't have a transition in between over here. All right, but you notice that the X values can have any arbitrary values. So I haven't shown you any ticks over here, and you notice that over here is jumping all the way up till here, but here there is a very small transition. So these X values could be any real numbers. And then finally, you have both X and time being discrete. In other words, you can only have transitions at certain pre-specified times, and also those transitions can't be arbitrary, they have to go between discrete values. So now you have these discrete values over here, as well as discrete values over here, and you notice that if you're jumping from here, you can go up till 3, but you can't go up till in the middle over here, and similarly, when you jump back, you can't jump back at any arbitrary time. You can only make changes at specified time intervals, and that you to only specified X values. Okay, so this is sometimes called a discrete time Markov chain. Okay, and now let's take a look at the next topic, which is basically what are Markov chains. So this is simply the case 4. Okay, so case 4 was the example of a stochastic process where time and X values are both discrete. Okay, before I go into Markov chains, let's just make sure that you 100% understand all the 4 cases. Can people give me any? We looked at several examples of this. Can people give me other examples of case 2, case 3, and case 4? Real world examples. G. Speak up a little bit. Case 2. For a football game. Okay, so the example given was that it's a football game which can either be, for example, stopped or continuing, or you could think of a third being that it's being temporarily, stopped because of a foul or something. But basically, it's 2 or 3 different values. So X is clearly discrete, and time is continuous because the fouls, for example, could happen at any time, and you could have a short interval where you've actually stopped for a foul. Okay, and then maybe you have a longer interval when you actually stop for breaks. So is case 2 clear? Okay. What about case 3? Can people give examples of case 3 where time is discrete but X is continuous? Changes can only happen at given times, but those changes can be any arbitrary. IBA schedule. So if you think about the IBA schedule, what are your continuous? Can IBA schedule be continuously varying? Unfortunately, it seems like it is. But is it supposed to be continuously varying? No, you can only have specified discrete values. In other words, if you look at the entire schedule, there are a certain number of professors teaching, and there are a certain number of time intervals. So I would think that the X values in a schedule are actually discrete. You can't have an infinite number of those. Think of another example, G. Traffic signal. Okay. So now in traffic signal, is the time continuous? Is the time discrete? Okay, yeah, so you can think of it that yes, if you can define your traffic signal such that it can only happen at every minute intervals. Okay, so you can, but in practice it doesn't really happen that way, but it does happen at the second interval. So it doesn't change at the half a second. Remember that when you look at the signals, it'll come up with 180 seconds, right? It'll start counting down. So it doesn't say 180.5. So in that sense, yes, you're right that the time is discrete, and X, now is X continuous or discrete? So X is discrete. So yeah, example is not very good. So you can either have, open or closed. So not a good example. Think of another example of case 3. Sorry? Depends on how you're defining the state. How are you defining the state in the traffic? What is the state? Stop it. If it's either stopped or go, then it's one of 2. And it's not discrete. But if you describe the state as the amount of traffic flow, in other words, how many cars are passing through or how many motorcycles are passing through, then it is continuous. because you can say that the average flow when it is open is 3.567 cars per minute. That's a real number. So then it depends on how you define your state. It can be continuous or discrete. Okay. So I'm saying that it depends on how you're defining your environment state, right? If you're defining your state as being the three values of your signal, which means start, stop, or about to stop, then your state is discrete. Okay. But if you're defining your state as not that, but a little bit more complex, which means that the amount of traffic, then at times when the signal is stopped, then your amount of traffic is 0. But when the signal is on, the amount of traffic can be varying between 0 to maybe 100 cars per minute or something. But your time will be perhaps discrete, because you're only changing at every second interval. But again, it's not a perfect example. I'll give you a simpler example. Okay. Think about the number of students in this auditorium. Number of students in any class, in a cafeteria, in an auditorium, in a room. Is the number sorry, that's not bad. That's a bad example. That was for case number 2. Okay, because the number of students can't be 3.5 students, right? It has to be the 3 or 4 students, and the time is continuous because the rate at which students are coming in, they could come at any time. So that is example 2. So coming back to example 3, where time is discrete, but x values are continuous. G. Of rain. Okay. Yeah. So we looked at this, I think yesterday as well, the other day, where you're saying that we're defining the time to be discrete. In other words, time is defined to be days. Okay. So you're going to say on the first day of the month, how much rain has fallen. Okay. Now the amount of rain fallen could be 0 till 100 millimeters or something, but it's a real number. And the time has been discretized. And we're saying that we're not looking at continuous time, but we're saying we're only looking at time intervals of daily times or yearly times or weekly. But we've defined time to be discrete. So it's sort of a choice. And you can define any system to be perhaps in any one of these 4 categories. It's how you model the system. So modeling is extremely important because the real world is extremely complex. Whenever you're converting it into a model, and that's what we've been doing right from day 1, is that we're trying to convert it into a model that can be analyzed. And we start with simple things and we make it more complex. And sometimes when you model a real world situation, the only reason you want to model it in a simple way is so that you can analyze it. Because if you analyze this rain problem in continuous time, it would look like something like this, and it may become very difficult to analyze. So sometimes, a lot of times what we do is we try to convert it into a discrete time, discrete value case, so that the analysis becomes simple. Okay, and as we go forward, we look a lot. In fact, the rest of the semester, we'll only look at this particular case, case 4, simply because it's easy to analyze. Okay, not because it's a very good reflection of real world, but simply because it's a good enough model of the real world in a lot of cases, and we can analyze it easily. Okay, G. Yeah, which example are you talking about? The number of students in a class? So number of if you look at the timetable, okay, so the number of, so that would be an example of maybe case 2. Case 2, why? Because unfortunately the time at which the schedule can change can be arbitrary, as you know, at IBA. At any time, day or night, the time can change. It doesn't necessarily have to change on a specific time interval, but you could convert it into a discrete time. You could say that actually it will change on a specific day of the month. So you don't really care if it changes at 4 p.m. You will approximate that as changing on the, let's say, the first day of the month or the second day. So you can convert that, even that problem, into case 4. Okay. Okay, so that's a slightly different problem. I was thinking of something else, but what you're saying is if your timetable is basically, but it's not evolving. Stochastic processes have to be something which is changing. So now if you're looking at your specific timetable and you're saying that over the semester, unfortunately, it does change, right? So in the first week, there are a lot of changes at IBA. Okay. So now those changes, are they happening in real time, in discrete time, or in continuous time? Actually, it's in continuous time, but you can model that as discrete time. You can say that actually it only happens on a specific days, and we will then try to model it as discrete time. Okay. So so let's continue on. I think you've got a rough idea. Okay. So now we look at so the last fourth case. Did we talk about a specific example of case 4? Let's think of a very simple example of case 4, where both of these are discrete. So again, let's look at the number of students in a classroom. But now I'm going to say what is the number of students, and I'm going to discretize time, and I'm going to say that this is, let's say, at 10 a.m. and this is at 11 a.m. and this is at 12 noon and this is at 1 p.m. So I've discretized time, and I'm only going to look. Somebody is going to come into this room every hour on the hour, and they're going to just count the number of students. Okay, so that you can think of as a discrete time case. Okay, discrete time, discrete values. So when the person comes in, the messenger comes in, he's going to find, let's say that right now there, let's say suppose 40 students in this classroom at, let's say 2 o'clock, 3 o'clock. Then he's not going to look at it in between times, but he's now going to come in at 4 p.m. and he's going to say how many people are there. Now that might be different, but it's going to be discrete, and now time has been discretized. Okay, so you can see that a real world situation, which was actually something like this, has now been converted into a discrete time problem. Okay, so hopefully if you've understood how we're modeling this, now we can look at some other examples. Okay, so this is a Markov chain, or discrete time Markov chain is something that can be modeled, has two properties. The first property is that it's going to be case 4. Okay, it's going to be case 4. In other words, both the x values and the time values are going to be discrete. That's the first property. Okay. The second property is that it's going to have something, special property called a Markov property, which we'll talk about in a little while. But let's first understand, let's take an example of this to be able to understand this better. So let's think about the rain example. Okay, not the rain example. Let's think about the weather example. Okay, so this is a weather in, let's say, Karachi. Okay, and we assume that the weather can be either sunny or rainy. Now you could think about it in more complex, it could be cloudy as well, but let's make it simple and let's say that it's either sunny or rainy. Okay, and what we're going to say is that the state now is either sunny or rainy, and we've discretized time and we're looking at time over days. Okay, so we're not looking at the change between sunny and rainy at 4 p.m. in the afternoon. We're simply going to say that on a particular day, are we classifying this, let's say on the first day of March, was it more sunny or was it more rainy? Okay, we'll classify it as one of two. So let's say it was sunny on the first day. On the second day of March, let's say it became rainy. And it was rainy for a couple of days. Then on the third day, fourth day, it became sunny again, became sunny for quite a while, then became rain for a day, and then sunny, and so on. Okay, so this is a simple, what is referred to as a Markov chain, and switching between two possible values, and this is a realization of x of t. Okay, so you can see that x of t is varying between two values and it's changing over time. Okay, so this is an example of a stochastic process. Now, this is one realization. You could have a completely different realization which has a completely different set of values, right? And the rest of it could continue to be different. So you could have another realization which starts off as rainy and sunny, and there's a lot of sun, and then there's a lot of rain. Okay, so you can have different realizations. Now, there's, in a Markov chain, you also have transition probabilities. In other words, what you say is that the probability of going from a sunny to a sunny day is assumed to be fixed, and the probability of going from sunny to rainy is also known, and this could be based on, let's say, the analysis of the last a year or last 10 years or 100 years or whatever. Okay, so for example, for Karachi, what do you think is the probability of going from a sunny to sunny day? If you have a sunny day today, what's the and let's assume that these are linked. In other words, that there is that these probabilities are not completely independent, but the probability of having a rainy day is somehow linked with the previous probability. Okay, so we're saying that it's not completely independent. Okay, these are conditional probabilities. So if you have sunny day on a particular day, what do you think is the probability of the next day being sunny or the next day being rainy? Can you think of examples for Karachi? 80% you're saying? Okay, so sunny to sunny is probably 80%, and so the sunny to rainy would be naturally 20%, would be 1 minus that. Similarly, if you have a rainy day, do you think the probability of a subsequent rainy day is again 20%, or is it going to be higher? Sorry? Is it going to be, so going from sunny to rainy was 20%, right? Now, once you've started raining on a particular day, do you think that the subsequent rain on a subsequent day is going to be the same, or is it going to be higher or lower? How many people think it's going to be higher? Actually, yeah. So the majority of you think that's going to be higher. Why? Because that, you know, that we have monsoons, right? So once the rainy season starts, it just doesn't stop, and you know that, right? We all live here in Karachi. Once it starts in the summer, and then you have a whole week of rain. Okay, so the probability of having rain on one day, what's the probability of having rain the next day? What should it be? So 70%. Okay, that's a good approximation. So this would clearly be 30%, right? 1 minus that. So here we basically formed a Markov chain. But what is our assumption? So now, remember that we've said that the probability of rain, the probability of sun to rain simply depends on where we're coming from the previous day. Is that an accurate model? You're shaking your head. Why? Okay, there are a lot of other factors, but let's just assume that we modeled our environment as only being one of two things, that the environment is either sunny or rainy. That's the entire thing. We're not modeling how many birds are going in the sky, etc., etc. Okay, it's a very simple model. That's the entire environment. But based on that, can you say, and of course these are also evolving over time. Now here we're saying that the probability that you go from sunny to rainy only depends on the current day. Now, is that a good approximation? Why not? Exactly. So actually, a more accurate approximation would be that what about the 2 days before? What about the whole week before, right? So I can't just say that the probability of going from a sunny day to rainy day is 0.2. Actually, this would depend not just on the current day, but it would depend on the previous day and perhaps the previous day and the previous day and so on. Okay. But that becomes a little bit more complex. Okay. And so this is where the Markov property comes in. The Markov property basically says, and this is, the model that we just made is what is referred to as a first order Markov chain. Okay. First order Markov chain. In other words, that the future only depends on the current state and not on the past. Okay, it doesn't matter where you're coming from. Now, given that you are on a sunny day, the future only depends on the current state. Okay, a second order Markov chain would say what? That the future not only depends on the current state, but actually depends on the previous state, and so on. You could make it more and more complex. Okay. So you guys thought of this. I made a slightly different approximation. I said that, well, sunny to sunny is, let's say, 90%, this is 10%, and rainy to rainy is 40%, and rainy to sunny is 1 minus that, 60%. Okay, so these are what are called transition probabilities. Okay, and you can show it as this. So sunny to sunny is 90%, sunny to rainy 0.4, rain to rain is 0.4, and the other is 1 minus that. Okay, so this is the transition probability table or matrix. Now the transition probabilities I've assumed are constant. Is that also a good approximation, or do you think that they might change over time? They might change, right? So, and we know that climate change is happening. So we know that in the past, when it used to rain in Karachi, well, you guys are young, but I remember when I was young, when it used to rain, the patterns were not the same as today. So over time, if you think about the lifetime, my lifetime, these probabilities have changed. Okay, and in the US, for example, hurricanes have become a lot more common. Why is that? So you're basically saying that the probability of sunny to rainy has become a lot higher. Okay, and so on. In England as well, things are changing. It's becoming, I think, a lot more rainy. Okay, so if over time, if the weather is changing, then these transition probabilities are also going to change. But we're going to make a simple assumption that these transition probabilities don't change, that the system is stationary. Okay, so stationary simply means, and this is not equal to static. Okay, static would mean that every day is a sunny day, but clearly that's not the case. We're switching between sunny and rainy days. Stationary means that the probabilities are not changing. Okay, that the probability of S going to R are not changing over time. Okay, this is just a fine point. It's not very important right now. Now, I spoke about the first order and second order Markov chain probabilities. So if you want to write it in this way, you could say that the future is independent of the past given the present. Okay, so if you say that, and here I'm going to use some notations, I could say that time at the future probability of X being equal to a particular value, or I might use a simple notation. Let's say the future value of the status of the day, okay, whether it's going to be sunny or rainy, could depend on, as you suggested, it actually not only depends on the current value, but actually depends on all the values, and I could put a dot, dot, dot over here. It could depend on all the past values, right from the day the Big Bang happened. Okay. So let's say that time started at a certain time. So the future could depend on all the past values. But if I were to say that the future is independent of the past given the present, how could we simplify this? Can we simplify this equation? So we're saying the future value is only dependent on what? On xt, exactly. So we're saying that we can actually neglect all the past values if it is a first order Markov chain. If it's a second order, then you would say that probability xt plus 1 depends on x of t and x of t minus 1. Okay, so this would be second order, and so on. You could make it more and more complex. So generally, we're going to assume a first order Markov chain simply because we want to make things simple. And that is simply called a first order Markov chain, or simply a Markov chain. Okay. So this is what you could say. This is the simpler way of looking at it, that you're going to neglect all the past values and it's only going to depend on the current. A slightly more detailed way of looking at it is this way, but basically means the same thing. Okay. Now let's take a look at some properties of the Markov chain. And if, let's say, you're given these transition probability values which we had earlier. Okay, so we have these transition probability matrix. Now what we're going to define is a steady state value, which means basically that what happens if you leave Karachi as it is, you go to the US or some favorite destination, and you come back on a random day to Karachi. And now you want to know what is the probability that it's going to be a sunny day or a rainy day. Okay. And my question is that given these transition probabilities, can we determine the probability that you come back at a random time? Can you determine the probability of being in a sunny or a rainy state? And my question is, from intuition, do you think that should be possible or not? Sorry? You're saying it should be possible, right? So you're saying that given that we know the transition probabilities, it should be possible that if we come back to Karachi after a long time, it's sort of in a steady state environment, right? It's been moving back and forth between sunny and rainy days very frequently. And you come back at a random time, okay? And you want to know what is the probability that it's going to be either in a sunny state or a rainy state, okay? And the answer to the question is yes. If you're given the transition probabilities, it is possible, okay? And the way it's possible is that there's something called balance equations. And I could try to derive that, and I try to give you an intuitive explanation of that. And let's see if I'm successful. But basically what this is saying is that let's define P of X to be the probability that we're looking for, right? The probability that it's going to be either sunny or it's either going to be rainy, okay? And this is the probability that Karachi is going to be either sunny or rainy, okay? Now, what the balance equations are basically saying that the probability of sunny, given that you're in this state, and the transition that you make from sunny to rain, you multiply these two values, this should be equal to the sort of the flux going in the opposite direction. Okay, this can be defined as the flux. So this is the flux going in this direction. This is equal to the flux going in the opposite direction. Okay, the flux in the opposite direction is the probability that you're in the state of rainy state, and you're making this transition. Now, this is called the balance equation, and it may not be very intuitive. I could try to sort of give you a rough idea why this is true, but you don't have to necessarily be able to derive this, okay? And a very rough idea of why this is true is because if you look at the number of transitions going upwards versus the number of transitions going downwards, are these on average over a long interval of time be equal? Yes. Why? Because if you look at the number of transitions going downwards, is how many times have you gone downwards? Twice. And you've gone upwards twice as well. So these two are equal in this hypothetical case. But what if I said that in the next state I went downwards, right? So you would say that going downwards has gone, this transition is now 3, and the upward transitions are only 2. But what if I keep on doing this for a very long time? What's the maximum difference between these two numbers? It's going to be 1, right? So if you went up, let's say n times, then the number of times you went down would either be n minus 1 or n plus 1, right? Because there are only 2 transitions. You're only going up or down. Okay? G. Okay. So what if you had, let's say, multiple states? All right. So let's say you're going upwards. In the previous example, let's say, I think we had an example over here. Okay. So if you take this example and you say that, what if I draw a line over here? Okay. If you draw a line anywhere across this, you can always convince yourself that the number of transitions crossing that line are going to be different at most by 1. Okay. You could take the crossing at any point over here or anyway, just try it out. Okay. The number of transitions, the number of times you're going to cut that line is going to be over a long period of time. These two are going to become approximately equal. Okay. So in other words, the number of transitions that you're going to make over here is going to be equal to the number of transitions you're going to make in the opposite direction over a long period of time. And what we're basically saying is that the number of transitions going in this direction is basically going to be the probability that you were in that state multiplied by the probability of making that transition. Okay, That should hopefully be somewhat intuitively obvious. The number of times that you're going to make this transition is the probability that you were in a rainy state, okay? Probability that you were in a rainy state multiplied by the rate at which you're going in the opposite, the probability of going in the other direction, okay? So these are often also called fluxes, okay? So the flux going in one direction is equal to the flux going in the other direction. But that's just to give you an intuitive explanation of this. And this sort of is one of the key aspects of a Markov chain, that given the transition probabilities, you can actually determine the probability of being in any given state. So the next question is, given this, can you now solve for P of S and P of R? So how many equations and how many unknowns? How many equations and how many unknowns? Remember that in any linear system of equations, the number of equations and number of unknowns have to be the same to be able to solve it, right? If you have two equations and two unknowns, you can solve it. But if you have one equation and two unknowns, then you can't solve it. So can we solve this? How many equations? So we're saying that the probability of going in this direction, the flux in this direction is equal to the flux in this direction. So that's one equation, right? So you have one equation and how many unknowns? Can we solve it? No, but do we know something else about these two probabilities? Yes, so actually they sum up to 1, because you can either be in a state, in the sunny state or rainy state. You can't have a cloudy state, for example, right? So the other equation is probability of sun plus probability of rain has to be equal to 1. So now you have another equation. You've got two equations and two unknowns, and voila, you can now solve this, okay? So you can simply solve this, and if you solve this using these two equations, you can get the probability of being in a sunny state is equal to 6/7. Probability of being in a rainy state is 1/7. Okay, does that make sense? So in other words, we're saying that this is 6/7 and this is 1/7. And you can see that it has something to do with these transition probabilities. Okay, the fact that you're going in this direction more often, okay, that means that the probability of this state becomes less probable, simply because as soon as you get into a rainy state, we're saying that there's a 60% chance that you will go back to a sunny state. And once you're in a sunny state, the probability of going into a rainy state is very small. So this becomes much higher. Does that make sense for Karachi? And you can test this out. You can use different probabilities, and maybe if you know what now the next question is, if you knew probability of S and probability of R, could you derive the probability of S to R and probability of R to S and so on, the transition probabilities? If you had these two, so let's say that we know that in Karachi, the 10% of the time it's sunny, sorry, 90% of the time it's sunny and 10% of the time it's rainy, or 99% time it's sunny and 1% time it's rainy. So can you derive the transition probabilities? Yeah, so it's not that easy. So the other way around, it's not obvious, okay? But you can derive their relationships. In other words, you could derive what is the ratio between the transition, for example, the ratios of these two, okay? But that's just something for your exercise. You can try to figure this out. So we've got some idea of what a Markov chain is, and we have some idea what it means by looking at a sunny and rainy situation. And of course, you could make it more complex. You could say, for example, that you have sunny, rainy, and cloudy days, okay? And you could have transitions between all three of these, and you could come up with a more complex model, okay? So you can always make it more and more complex. It would still be, would this still be a Markov chain? Would it be a first order Markov chain or second order Markov chain? It's still a first order, because we're now saying that the number of states is now increased to 3. Okay, but it's still a first order. In other words, the transition from S to R only depends on S. Okay. So now let's start. We've got another 15 minutes. Now we're going to make the model more complex. Okay. So brace yourselves. So now we're going to look at what is a Markov decision process. Okay. Now the first question is, isn't this complicated enough? Why do we need to look at Markov decision process? Okay. Well, the reason why we need to look at Markov decision process is, if you think about what we've done so far, is we've forgotten about our searching agent. Remember our environment where we started off this course? We said we have an agent, we have an environment, and we have a search problem, and we're trying to solve that problem. Okay. And we've gone through different stages of this course where we've made things more and more complex. Okay. We said that, for example, we were going through a search state, and we said that there could be probabilities involved in making certain decisions, or it could be non-probabilistic. So when we added probabilities, it became more complex. Okay. So now we sort of going one step further, and we're saying that, can we make our environment more complex and make it be a Markov chain? Okay. So essentially what we're saying is that the environment now, for example, if you're trying to model the weather, can we make the environment a Markov? Can we model that as a Markov chain? And now can we make decisions as to perhaps what we should do? Okay, whether we should carry an umbrella, or should we go to IBA with an umbrella or not, depending on what is our probability of it raining today or not. Okay, so we need to be able to interact with our environment with actions. Okay, and the environment could be more complex. It could be actually be a Markov chain. And the other complication that we're going to introduce is that, remember that when we're playing a game, okay, and we take a certain action, did our action always result in a deterministic response? Remember, where was that case where our action did not have a deterministic response? What are all those cases? We tried to do, we were playing chess, we took one action, and the next action depended on the opponent, right? So there was a 20% chance, example in the quiz as well. We said that Y, if you're X and you're taking a particular position, and you know that Y will respond in a certain way, there's a certain probability that Y may not choose the optimal decision. Okay, so your actions may not necessarily always result in a predictable outcome. Okay, so these are the complexities that we're going to build into our next model. Okay, number one, that the environment can be modeled as a Markov chain. Okay, we already know what a Markov chain is, and it's a more complex model of the environment. Number two, we're going to assume that whatever actions we take will not always have a deterministic response. Okay, these are the two things that we're now going to take as we go forward. So let's take a look at how can we actually model that. And it's going to be a complex model, but we'll use some simple examples to be able to try to explain how a Markov decision process works. Okay. So this is a Markov decision process. It's an extension of a discrete time Markov chain. What's a discrete time Markov chain? What we just studied, Markov chain of the sunny and rainy days. But now we're going to introduce an agent and an environment. Okay. So the agent is going to obviously take certain actions based on the environment. And the agent is also going to get certain rewards. Okay, remember the utility. We're trying to maximize utility. So an agent which doesn't have any rewards, but doesn't have any utility is, somebody who's actually looking at, he's got a problem, a solution without a problem. Okay, not very good to be in. You need to have a particular problem in mind. So you need to have rewards and you need to have actions. So those are two things that we're going to have. The environment, of course, is going to be modeled as a set of states. Sort of we've already been doing that. We're going to say that the set of actions that the agent can take is given by A. Now, as I said, the result of your action is not going to be deterministic. Okay, so you're trying to go in a particular direction, but there's a certain probability that you'll go in that direction, and there's a certain probability that you might go in a different direction. Okay, we've sort of already seen that. So we're saying that given that you're in state S, it could be sunny or rainy, what is the probability that you go into a different state depending on the certain action? So we're introducing actions now. Okay, so this is a notation which simply says, given that you're in a certain state and you take a certain action, what's the probability of going into a subsequent state? Okay, slightly more complex than a Markov chain. Because why is that? Because now we've introduced an action as well. Okay, and we're also saying that there are going to be rewards. Now let's take a look at a simple example before it becomes too complex. So let's say that you try to climb a tree. Okay, three possible states are S1, you're on the ground, S2, you're in the middle of the tree, and S3, you're at the top of the tree. Okay, there's a nice apple at the top of the tree. Okay, and so the reward, if you get to the top of the tree, is +2. If you get back to the ground, yes, you're on the ground, that's nice to be there in a stable environment, so the reward is simply +1. Okay, and you start off, your starting state is in the middle. Okay, you start off somehow, you're in the middle of the tree. Okay, and you can take two actions. You can either try to go up or you can try to go down. So the possible actions are up or down, right? So far so good. Possible states are three states, S1, S2, and S3. Starting state is in the middle of the tree, and once you're at the top, you're going to stop over there, and once you're at the bottom, you're going to stop over there. So it's a very simple scenario. These are terminal states. Okay, the game is over. You get to the top, the game is over. You get to the bottom, the game is over. So let's try to see. Let's say that the probability of, now once you take an action, let's say that you take an action of going downwards, it results in an intermediate state. This is called a Q state. Okay, once you've decided to go in a particular action, you get into a Q state. Now you haven't really taken that action. Okay, and afterwards you take that action, and now what we're saying is that if you're trying to go down the tree and you decided to go down, then the probability of getting down is hopefully is going to be 1, right? There's only one way you can go. However, when you're trying to go up, you've decided that, no, I'm going to go for the apple, right? So I'm going to try to go up, and now you're in this Q state, and now I'm saying that there's a certain probability that you might actually slip and get down. Okay, so you're trying to go up, and anybody who's climbed a tree knows that you can slip. Okay, and you end up at the bottom. So let's say I'm saying that there's a 20% chance that you slip and you fall down, and there's an 80% chance that you end up at the top of the tree. Okay, so let's just convert this problem into our probabilities. Okay, so this is how we're going to say that given that you're in state S2, the probability of going into S3, given that you take the action up, is going to be what? 80%. All right. Given that you're in state S2, the probability of getting into state S1, given that the action is up, you're trying to go up, what's the probability you'll end up in state S1? Is 0.2, right? So it's simply trying to understand those probabilities. What's the probability of this? Is 1. Clearly, there is no, this has not been considered. Okay, so I'm not looking at this. So when you're trying to go down, there is a probability that you're actually going to end up. That's going against gravity, right? So we're going to say that if you're trying to go down, then you can only get to state S1, and that's 100% probability simply because of gravity. Okay, you can't miraculously somehow jump up. Now, what would be the rewards over here? What's the reward given that you're in S2, you're trying to get to S3 and you taking the decision of going upwards? What should be the reward over here? That's a +2. Okay. And another way of framing this is, well, let's look at this. What should be the reward if you're going from S2 to S1? And I'm saying that regardless of where you get going from, in other words, regardless of what action you take. So in other words, either if you try to go downwards or you try to go upwards and you slip and you come down, what is the reward over here? It's going to be +1. Okay, so you can see why I've put an X over here, because there are two possible actions that could lead you from S2 to S1. It could either be you trying to go downwards, or you trying to go upwards and you slipped and you fell, went down. Okay, so this is +1. Okay, so far so good. You've understood the notation. Now I'm going to introduce something else, and this is going to be the cumulative reward, okay, of taking particular action. So now what we're going to introduce is several things before I introduce the Q value. So the first thing I'm going to introduce is a policy. Okay. Now policy simply means that the policy pi in a particular state is the action to take in state S. Okay. So in other words, if you're in state S2, if you're trying to maximize your reward, what should be your action? Going up, right? Because you could go down, but that's sort of given, is +1, right? But if you try to go upwards, what is the reward that you can actually get? So that's going to be given by here. What's the reward that you can get when you go upwards? Is it definite +2? No, it's going to be, how are you going to calculate the expected reward? 0.8 times 2 plus 0.2 times 1, right? Why is that? Because there's a 20% chance that you might actually get down. Okay, so the probability of the Q value or the reward, the cumulative reward that you can get if you take the action going upwards from state S2 is actually 1.6 plus 0.2 is 1.8. Okay. What's the Q value? What's the cumulative reward if you want to, if in state S2 you decided to go down, you took this action? Clearly it's 1 because it's 100%, right? So now my question is, what is the optimal policy? The optimal policy is defined as determines the action in every state that maximizes the expected cumulative reward. Okay. So basically what we're saying is that if you're in state S2, what should be your optimal policy? In other words, what will maximize your reward? Trying to go upwards, right? So clearly the optimal policy over here is simply up. This is the action that you're going to take. Okay. So Q value is basically the action that you will take. The pi star is simply the action that you will take that will maximize your Q values. Okay. So in this particular example, it was fairly straightforward. Let's take a slightly more complex example. So this is something that I already sorted for you. Now here's a more complex example, and we'll continue this on in the next lecture, but let me just start it because we do have a few minutes. Okay, 3 minutes. So how many of you have cars? Does anybody own a car? Okay, so how many of you have actually tried to maintain your own car or your parents' cars? Okay, hopefully some of you. So you know that there's always a trade-off, that the question is that if you get a new car, should you actually pay for regular maintenance? Let's say you have a Toyota, and every month or every quarter, should you actually pay for that maintenance? And what does that help you? That's sort of a decision you have to need to take, right? If you're paying every month, how much does it cost? Does it cost every quarter to maintain it from, Indus Motors or something? It's fairly expensive, right? Maybe about 5,000 rupees every quarter. Okay. Now, if you maintain your car, then why are you maintaining that? Because you think that hopefully your car is going to remain in a good state. Okay. But if you don't maintain your car and you say, well, why should I spend 5,000 rupees every quarter? I'm just going to take the risk and I'm not going to do maintenance. But then what's the risk? The risk is that probably your car is going to get broken down and get into some kind of a problem. And I'm going to call that a poor state. Okay. So I'm basically saying that let's model our car as having one of two states. Now, obviously, it's a very simplistic model. The car could actually be considered as one of thousands of states, right? It could have, you know, the engine breakdown or the tires broken down or something else, right? But let's simply say that it's either in a good state or a poor state. Okay. So here's our car. It's either in a good state or a poor state. Okay. Now, what I'm saying is that in a good state, you could either take an action, could either be, so the states are good or poor, you could either take the action of maintaining the car, right? Or you could decide, what the heck, I'm not going to maintain the car. Okay. Now, if you're maintaining the car, there's a certain probability that the car will remain in a good state. And there's a certain probability that it would break down in the next quarter. Okay. Now, if you're not maintaining it, I wrote this down, but if you're not maintaining it, there's again a certain probability that it's going to remain in a good state or it's going to break down. Now, which of these do you think is more probable? If you compare, let's say, this transition with this transition, which of these will be more likely? If you're maintaining the car, hopefully the probability that it's going to remain in a good state is going to be higher. Okay. So let's say this could be 0.9. And the probability that if you're not maintaining it, it's going to be lower, right? So the original that example I had over here was 0.5. So there's a lower probability that it's going to be in a good state. Okay. Similarly, if this was 0.9, what's the probability that it will actually break down? It's going to be 0.1 simply because it can go in one of two ways. Similarly, if you're maintaining it, if you're not maintaining it, the probability it will retain in a good state is 0.5. Again, the probability that it will go bad will also be 1 minus that will be 0.5. Okay. So this is an example. Since we kind of over our time, let's continue this example and try to see if we can develop this model and try to see what kinds of decisions would we end up making if you actually had a real world scenario like this.